Previously, I had made a video about the difficulty I was having in understanding isotope exchange and isotope fractionation. I have put a link to that previous video in the description. We've made some progress since then in understanding. A few questions still remain, but we've made some progress in getting a better understanding, a better visualization of the processes involved. And before I dive into that, I'd just like to do a very quick recap of the previous video. I'll just go into slideshow. This is the equation that we had encountered in Emerson and Hedges, 2008, page number 142, 144. He had divided these into two half reactions, heavy isotope substitution, the one that you see on the left side, and the light one on the right hand side, and subsequent constituent forward and backward reactions. Then over here I had reacted 8 12CO2 and 8 13CO2 molecules with water, leading to 8 H212CO3 and 8 H213CO3. And then these had, out of these 8, 4 had broken back into H2 and 12CO2 and their respective water and 13CO2 molecules to form the backward reaction. I was having trouble in putting this all together. And so we've, as I said, I've made some progress since then. So we will revisit the first slide, and so this was the main reaction and the subsequent heavy isotope and light isotope substitutions. And the mistake that I was making here was that I was reacting an equal amount of both with water. That was one mistake. The other mistake I was making here was that I had taken an equal amount of water. Water in practice and reality is infinite. So we'll work with this added information, a somewhat better understanding of the process, and we'll dive back into it. So we have infinite water, and 13CO3, the heavy isotope, is like one of those people who takes time to form friendships, but when it does form friendships, it takes time to break up. The lighter isotope is like one of those extroverted people who talk to everybody and make friends quicker, but they also drift off just as easily. So we'll work with that understanding. And I'm going to react 12 CO2 molecules with water, leading to 12 H2 13CO3. And do note that the water is infinite here, so that's a change from the previous slides. Then I'm going to react 8 instead of 12. I'm going to react 8 13CO2 molecules, leading to 8 carbonic acid molecules with 13 carbon. Now, the change that I'm going to do is that out of these 12 H2 12CO3, I'm going to break up 6 into carbon dioxide and water. So that is 50%, 6 out of 12. And out of these 8, I'm going to break up 2, which is 25% of 8. So whatever amount that 12CO2 reacted with, 50% of it was, so to speak, unsustainable and broke off just as quickly as it was made. And even though only 8 molecules of 13CO2 reacted at first, only 2, that is 25%, broke off. The rest 6, that is 75%, stayed there. Okay? And now we have an equal amount of both. We have 6 over here and we have 6 over here. Now we'll go back to the first slide. And I'm going to add an intermediate step here. And this is going to hopefully improve our understanding. I've added this step, and this is what we actually started with, if you think about it. This was the initial, the original, the time zero state. This is what it was. This is what we started with. Now, if the reaction moves in this direction, you have 12CO2 reacting with H2, leading to H212CO3. Oops, sorry. And if the reaction moves in this direction, you have 13CO2 reacting with H2, leading to H213CO3 and 12CO2. So, contrary to the impression that this gives, carbon dioxide molecules are not colliding with carbonic acid molecules. There's this intermediate step that's taking place. Carbonic acid is disintegrating, dissociating into its constituent carbon dioxide and water molecules. And then, of course, then this portion, the backward reaction would be going in this direction, leading to, again, 13CO2, 12CO2, H2O, and the same holds true for here. So let's go back. This is where we had left off. We had 6 carbonic acid molecules with 12 carbon and 6 carbonic acid molecules with 13 carbon. Let's react another 12 CO2 molecules, leading to more 12. So total of 18 H212CO3, and we're going to react 8 just as we did it previously, leading to 8 more. Okay. Now you can see that this is 18 and this is 8 plus 6, 14. But out of the 12 that we reacted just now, the light isotopes, 6 are going to break off 50%, just the same rate that we had taken in the previous slides, and they're going to go back, and we're left with 12 here, and over here 2 are going to break off and go back, and in the end we are left again with 12. And no matter how many times we repeat the same thing, and no matter how many more CO2 molecules I take, we'll end up with the same once the backward reaction manifests. So I'm not sure what mistake I'm committing here. Should I be breaking up less? A less number of H213CO3 molecules and breaking up more of H212CO3 molecules in order to accurately represent what goes on in reality? That could be one thing. But this does raise a few questions. The first question is, of course, something which I addressed previously. When you write this reaction, it's not as if the carbon dioxide is colliding directly with carbonic acid, which is what it theoretically seems like the way it's written on paper. And in reality, there's an intermediate step going on. Again, I hope I'm correct. The next question, I'm going to skip 3, the question number 3 for now. I'm going to take it up in the next video. Question number 4 is, if the water is infinite, first of all, why are we taking it as infinite? Is that's a more accurate representation of reality? Number 1, that's something I do understand, but what I don't understand is, why is this thing important? Even if I had taken the same number of water molecules as the carbon dioxide molecules above the water body, what difference would it have made? Because if the water is indeed infinite, then there are enough water molecules for both 12CO2 and 13CO2 to react with. So why the fuss over fractionation? The example that I was given with in the last meeting was that, let's imagine a train coach which is reserved for women, and let's assume that the men have taken up all the seats. So when the women enter, they ask all the men to get up. Something of that sort. Or a train coach that is occupied by some young college kids, and then a contingent of businessmen comes in and they ask them to move to the side. Now, that is a plausible explanation if the number of seats are indeed limited. But over here, there was enough water, there was enough seats for everyone. So with a fractionation, what's the fuss over fractionation if there's really enough for everybody? I'm gonna leave there, and even though I haven't gotten a complete understanding of the process, I think this is somewhat of an improvement. We've progressed a little bit from where we were earlier. So I'm going to end the video here, and hopefully we'll address this in the next upcoming videos.